Well, students, yesterday we learned about electronic configuration of elements and we followed certain rules like Pauli's exclusion principle, then Horn's rule, and APA principle or APA rule. This table is APA table. This gives you an idea of energy of orbitals, that is, orbitals having lower energy followed by the orbitals having higher energy. And while building up electronic configuration of elements, we proceed as these arrows proceed one after the other. But yesterday I told you that there are certain elements which do not obey this table fully, completely. Up to some extent they do obey, but at certain stage they don't. Now today we will discuss why, and if they don't obey this table, then how their electronic configuration is built up. So here we will discuss a term that is stability of half-filled and completely filled orbitals. To understand this concept, let us take an example of electronic configuration of chromium. Chromium has atomic number of 24. If we build up its electronic configuration according to this table, we will proceed like this. 1s2 first, then another arrow falls on 2s, 2 electrons to it, followed by 2p6, 3s2, 3s2, then 3p6. Let us count number of electrons. 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18. We have 24. So we will proceed further. After 3p, there is 4s, 2 electrons. And after 4s, I will have to go to 3d. 3d, d can accommodate as many as 10. Now let us count how many electrons we need to fill up more. 2 plus 2, 4, 10, 12, 18 and 2. 18 plus 2 means 20. So I need only 4 to get 24. This should be the electronic configuration as per this table. But this is wrong. This is wrong electronic configuration. Now the reason for this wrong electronic configuration is, here we find this 3d orbital has 4 electrons, which is not half-filled. If it can get one more electron from somewhere, it can become half-filled. Why half-filled? Because if it gets half-filled, it becomes more stable. So I mean to understand that half-filled orbital and completely filled. I will come to completely filled later on. But as far as half-filled orbitals are concerned, this is a typical example of half-filled. So if I take one electron from this and it comes to this, we will get like this. 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 4s, 4s1, and this one electron will go to this d, making it 5. This becomes electronic configuration of chromium, and this is the right electronic configuration. Now the reason is why this happened. There are two things in it. One is symmetry. And another is exchange energy. and stability of orbitals that depends upon these two factors. More the symmetry, higher is the stability of that electronic configuration. Now what is symmetry? How symmetry leads to higher stability? Now I will go back to this example. Here this is 3d4. This is not as stable as 3d5 because 3d5, this 3d5 is half filled. Half filled orbitals are more stable as compared to others. So that is why, and when it gets half filled, it gets more symmetry and hence more stability. So symmetry leads to stability. So this is one of the factors for the fact that these orbitals which are half filled or completely filled, I will come to completely filled later on, but half filled orbitals are more stable. So one factor is symmetry, more symmetry, higher stability. And another is exchange energy. Now what we mean by exchange energy? Exchange energy means, suppose this is an orbital, say it is p subshell, and as you know, p subshell has how many orbitals? 3 orbitals. So the orbitals in the same subshell, they have almost equal energy. They have almost equal energy. That by energy I mean electron. For example, it has 5 electrons. 1, 2, 3, 4 and 5. These are electrons. That means this is the energy of these orbitals. This energy can, these electrons can exchange energy within the same subshell. That is within these orbitals. They can exchange energy. So if they exchange energy, that energy is known as exchange energy. Higher the exchange energy, higher will be the stability. So when one electron from 4s1 that goes to 3d, making it 5, here what happens? This energy, that is exchange energy, that increases. So when this exchange energy increases, that orbital becomes more stable. The electronic configuration becomes more stable. So this is another factor, that is exchange energy. Now there are two types of energies here. One is exchange, one is orbital energy. Orbital energy means when electron is here. This is orbital energy. But when it comes to 3d orbital, it becomes what energy? Exchange energy. So here exchange energy is more. Exchange energy is more than what energy? Orbital energy. So when exchange energy is more than the orbital energy, that becomes more stable. So there are two main factors for the stability of half filled and completely filled orbitals. So I will move back to symmetry. More symmetry, higher stability. More exchange energy than the orbital energy, more stability. This is one example, that is chromium. I will take another example. Say copper. I will take another example of copper. Copper, atomic number 29, and its electronic configuration as per ABBA table will be 1s2, 2s2, 2p6, 3s2, 3p6. After 3p we shall move to 4s, 4s2. After 4s I will move to 3d, 3d10. Now let us count first. 2 plus 2 4, 10, 12, 18, 18 plus 10 28, 30. So I need to put only 9 electrons here, not 10, so that I get 29 electrons. Now again, Here again, this orbital, that is 3D orbital, it has how many electrons? 9. I am coming to the case of completely filled now. In the first case, in case of that chromium, I had taken half filled. Now this time I will be taking completely filled. Now see, if this D gets one electron from this 4s orbital, then it gets 10 like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 1 electron will go to 3D, making it 10. Now this 3D orbital becomes completely filled. This is example of completely filled orbital. Here in this case also those two factors come into play. That is one factor, that is symmetry, which I just discussed. Symmetry, and other was, if you remember, it was exchange energy. In this case again, when one, so this first case, this is wrong. I will just tell you why it is wrong. And the second one is the right electronic configuration of copper. Now why this is right and this is wrong? Again, these two factors are responsible for this. When this 3D orbital becomes completely filled, when one electron comes from this and moves to 3D, making it 10, what happens? It becomes more symmetrical. And when it becomes more symmetrical, its stability increases. It becomes more stable. Again, as far as your exchange energy is concerned, now again one electron from 4s that moves to 3D, making it 10. What happens here? The orbital energy becomes lesser and your exchange energy, this exchange energy increases. Higher the exchange energy, higher will be the stability of the higher will be the stability of that very atom. So the copper has this electronic configuration instead of this. So again, what we conclude from these two examples, that half filled orbital and completely filled orbitals are more stable. I can take some other examples also. For example, I have an element molybdenum having symbol MO. Its atomic number is 42. Let us make its electronic configuration as per Oppa table. I will get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I am proceeding as per Oppa table. 3d10. After 3d10, this is 3d, I will move to 4p, 4p6. After 4p, 5s. I will keep these vacant, 4d and 4f. Why? Because as per Oppa table, after 4p, I have to move to 5s. Now, before moving further, let us count the number of electrons. 2 plus 2, 4, 10, 12, 18, 18 plus 10, 28. 28 and 2, 30, 30 and 6, 36, plus 2, 38. How many electrons I now require? 4. After 5s, I move to 4d. This is 4d. How many electrons are required? 4. And now it is 42. So, electronic configuration as per Oppa table of molybdenum having atomic number 42 is this. But again, this is wrong. Why wrong? Again, this factor 4d. 4d has how many electrons? 4. If it gets one more, it becomes half filled, and if it becomes half filled, it will become more stable. It will have higher symmetry. its exchange energy will be more than the orbital energy. So its right electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d5, not 4. And here I shall get only 1. This is the right electronic configuration of molybdenum having atomic number 44. Again, those two factors come into play. One, the higher symmetry, and another higher exchange energy, in this case as compared to this. Higher exchange energy than the orbital energy. This is one more example of this stability of, this is completely filled. This is not half filled. Now, I can take another example of completely filled. Say silver with symbol Ag, and its atomic number is 47. Let's make its electronic configuration as per Obba table, like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. After 4p, 5s, 5s2. After 5s, 4d, 4d9. I think I have got 47. Just count. 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18, 10, 28, 30, 36, 36 and 9, 45 plus 2, 47. Here again, take this 4d. This is not completely filled. It has got 9 electrons. If it gets 10, it becomes completely filled. And when it gets completely filled, it acquires more stability. So, its right electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, not 9. And this will be 5s1. Again, what happens in second case? This is the right case. The first one is wrong electronic configuration of silver. Here, why wrong? Because in second case, I have got completely filled 4d orbital, and thus it gets this gets more exchange energy, more symmetry, and therefore higher stability. So this is right electronic configuration of silver. So we conclude that there are some exceptions in electronic configuration of these elements. For example, molybdenum, here silver. In the first case, I had taken chromium and copper. These are exceptional electronic configuration, because what happens in these cases? In these cases, two factors. Please remember, two factors come into play. One is symmetry and another is exchange energy. So we conclude. Thank you very much.